When modeling things in algebra, we use something called variables. Now, variables are stuff like x, y, z, so on. We represent them using letters, usually. And, well, okay, sometimes we use letters that aren't English letters, so maybe alpha or omega or whatever. But usually they're used in terms of just English letters. The point of a variable is that we don't know what it is. So the value that it can actually be, well, since we aren't sure, it's able to vary. Very able. Let's think about where the word came from, right? The etymology, i.e. the origin of the word, should be quite obvious. So an algebraic expression is a math phrase. So it's made out of numbers and variables. Technically speaking, you can say that it's made of numbers and or variables. Why? Well, let's think about this. If we have a situation where we're representing just x. So I walked x meters east. How far east did I move? X meters. So is there a number written there? Well, actually, that's 1x. We just don't write the 1 because, well, x is just x. And, well, wait a second. What if I'm talking about how far west did I move? Then I went negative x west because I went east. Right? So, negative x, that's technically speaking, that's negative 1x. But we don't write the 1. Of course, something like 11, we write 1, x, right? Because 11 is 1, 1. So, for example, this here, we have an algebraic expression. We have a coefficient on the variable. The 7 is the coefficient. And then we have a constant. And then we have variable over here. So, coefficient, constant, variable. Alright. This might model a real-life situation. An algebraic expression in general can be used to model real-life situations. For example, you can say, I ran 3 times around a pond. And then I ran 10 more meters. I don't know how far it is around the pond. So I'll put that down as x, unknown. So that would be 3x plus 10. In this case, 7x plus 10 might be the case that you ran around a pond 7 times in a week, probably. And then you ran 10 more kilometers. Why is it 7 times in a week and then 10 more kilometers? Because to say that today you ran around a pond 7 times and then 10 more kilometers sounds a little bit iffy for the simple reason that, well, okay, of course it depends on how big the pond is, but to put kilometers in conjunction with running around a pond usually means the pond is at least within reasonable shouting range distance-wise. It's not like just a hole in the ground with a little bit of water in it, and then you walk around it 5 times and then run 10 kilometers. You probably wouldn't even consider that when you're calculating how far you ran, right? Wait a second. This is math. This is not applied to reality per se. This is modeling reality. That means that this pond might indeed be just a little hole in the ground that is like, going around it is 0.001 kilometers, i.e. 1 meter. And then you ran 10 more kilometers. There's nothing wrong with this in terms of algebra, even though in real life you would not model it like that. Now, suppose that this is mowing a lawn. So to mow a lawn, you are paid $10 and $7 per half hour you spend on it. So you can choose to spend 1, 2, or 3 half hours. What gives you the best return? the best income? You would prefer to do the fastest lawn first. Why? Because $17 in half an hour is much better than $24 in 1 hour. Or $31 in 1.5 hours. Now, we will use some algebra tiles, which are commonly used in North America, to teach people how algebra works. Even though a lot of it will look very similar to, if not completely overlap with, number tiles. Now, a common convention for algebra tiles is colored in is positive, but white or blank ones are negative. Now, of course, on this, we will have filled ones be positive. So when we draw them, we can represent them like this. And blank ones be negative. Now, what do these two add together to be? Oh, look, plus, say 1, or maybe it's 1x squared, minus 1. If we add 1 and then we take 1 away, nothing changes. So these can be removed. They can cancel each other out. A unit tile represents 1 by 1 in modeling. So it has an area of 1. It has a length and width of 1. And it represents a value of, hopefully unsurprisingly, 1. Now, if you have a constant term that is bigger than about 20 or so, tiles of 10 may be a good investment. Just because drawing 20 unit tiles is a bit of a pain. But then you would have to label them as 10, 1, or something like this. Now, an X tile is a rectangular tile. It is used to represent the variable X. So X, 1. Now, when you do this in school, often you will use X tiles of 10. For the simple reason that when you buy number tile sets, it's better to use that tile set for both, say, elementary school and for high school students. It's cheaper. And you can't exactly make these tiles very easily by having them actually able to change length, because the value of X is variable. And not to mention, sometimes you get X is negative. Well, wait a second. How do you model a negative area? You don't. Or alternatively, you model it using negative X being positive. Now, I realize this might sound kind of confusing, but wait a second. What if X here is negative 5 or something? Then this area would be negative 5. It would be positive X, yes, but it would also be negative 5. Which means that when you model it, things get a little awkward. Thankfully, by the time we get to X being negative, we will not be using algebraic modeling anymore. Hurrah! Or mostly not. Because that really gets in the way when you start doing X squared. Because X squared is always going to be 0 or larger. So strictly non-negative. This is an unknown area. It is X units by X units. Now, this is the unknown squared. There are also Y squared and maybe Z squared tiles that you can work with, especially in, say, geometry software, but we aren't going to use those for now. As with X tiles, often when you model this in school, in class, you will end up using standard number tiles, which means that this comes out to the 100 square. Volumes. Volumes can be modeled by linking cubes or by stacking little 1 cubes. Because, well, wait a second. The number modeling kits the number tile kits usually come with cubes for ones instead of squares. Why? Because when kids are being taught how to add thousands, they use a 1,000 cube, which is 10 on a side. Volume modeling, the linking cubes we're talking about here, well, you've probably seen them at school at some point. But do remember that the number of cubes is not indicative of the value of x, y, or whatever variable you're using, because it's just a visual thought illustration, so to speak. Do not become confused on this point because it makes for some really dumb mistakes. State the length, width, and height of each representation. A unit tile has length 1, width 1, and height equals 1. Even if your unit tiles are flat, the actual value they represent is 1, and therefore 1 times 1 times 1 is equal to 1. An X tile has length of X, width of 1, and height of 1. So X times 1 is X, and then times 1 again is still X. Thus, the volume that this represents is X. Or, if you're working in 2 dimensions only, you don't account for the height. So if they don't ask you for the height, then assume you're working in 2 dimensions, in which case you can omit height. X squared tile, length equals X, width equals X, and height equals 1. X times X is X squared, and then 1, well, X squared times 1 is X squared. X to the 3rd volume. That just means multiplying another X onto this chain of X's. So for example, the cube, that is 1,000 little cubes. That's 10 little cubes times 10 little cubes times 10 little cubes. Hence, it is 10 to the 3rd power. Example 2. Alright, what expressions are represented by these algebra tile models? We're using the hollow negative filled positive convention. So up here we have negative, because hollow is negative, negative x squared, and then negative x. So you can think of this as being, this is like plus negative x. You can think of it this way if you want, but in general we prefer to go straight for the finish instead of taking this mental loop. Here we have filled positive. That means this is positive x squared plus 2x. Now why is it that we say this is plus negative x? It's because clearly we're putting this next to this, we're adding them together. We're putting them together, we're adding them in this case. So plus negative x. Here it's just plus, well, positive 2x, therefore we don't need to consider this sort of thing. And then minus 1, or plus negative 1 if you really want, but in the end you have to simplify to this anyway. Now, how do you represent the following situations with algebra tiles? Here, 3x squared one, 2, 3 x squared. Well, it's positive 3, so all of these are filled in. Minus 4x and then plus 2. What next? Well, we have a situation. A person walked 3 times an unknown distance east of their home. Then they backtracked, in this case walked west, so they followed their tracks backwards, hence backtrack, the word. One unknown distance. So represent this situation. Then indicate the algebra diagram where you can simplify this. Well, wait a second. So we went, 3 times the unknown distance east. And then we went 1 unknown distance west. So negative here. How can we simplify this? Well, we can remove this. Because plus 1 minus 1 equals plus 0. Plus x minus x equals, well, it also cancels out to nothing. No change. Alright, example 4. Build an area model with tiles. The length of the width of the area are as indicated. What is the area? What mathematical property does this demonstrate? Well then, here we have length x plus 5 and width of x. Okay, let's start with an x squared. And then length x plus 5. Well, 1, 2, 3, 4. I know I could have drawn all of these at once and then separated it, but this illustrates it well enough. 5. So, what is the total area? The total area is clearly, x squared, because there was 1x squared, plus 5x. Now, what does this start with? This is from x times x plus 5 equals x squared plus 5x. Now it looks like we multiply x by x and then we multiply x by 5 and we added them together. Or plus 5 in this case, and put them together. That's exactly how these works. So that's distributive property. Length x plus 2, width x plus 1. Well, okay, that one a little bit over. So, what do we have here? Well, x plus 2 times x plus 1. Clearly, we have, x squared first. So we take this x term, and then we multiply by x plus 1, and that gives us x squared plus x. And then we take this plus 2 over here, and we multiply by x plus 1, and we get plus 2x plus 2. So this is equal to x squared plus 3x plus 2. Now example 5. This may be found on math contests. Find the smallest possible value of a to the power of b plus c to the power of d plus e to the power of f plus g to the power of h if each letter is different and chosen from the values of 1 through 8. Well, here, how do we make the value of an exponent as small as possible? Well, we know that we want the 8 to be used either as a root base or as an exponent for 1. So say 1 to the 8th, because 1 times itself 8 times is going to be 1. Plus, okay, so we want to couple the biggest exponents to the smallest numbers, or the smallest exponents to the biggest numbers, which means that for 2, this could be 2 to the power of 7 or 7 to the power of 2. Now the reason why 1 to the power of 8 was used instead of 8 to the power of 1 is because 1 is smaller than 8. Now this second step though, 7 to the power of 2, 7 squared, is only 49. 2 to the power of 7, on the other hand, is 4 times 32. 32 is 2 to the power of 5. So this is going to be 7 to the power of 2 plus 3 to the power of 6 versus 6 to the power of 3. Well, the thing is, 3 squared is going to be 9. 3 groups of 3 squared multiplied together is going to be 9 to the power of 3, which is clearly going to be bigger than 6 to the power of 3. Plus 5 to the power of 4. Now, this is the smallest possible value of this expression. Evaluating it is a matter of just pushing buttons on a calculator. So after some button mashing, we get equals 1. Okay, that's obvious. Plus 49 plus 6 to the third is 36 times 6, which is then 216. Plus 5 times 5 is 25, and that squared is 625. Actually, button mashing is optional here, as long as you remember some of the basic powers. And adding this together, well, I don't particularly feel like adding it by mental math. And honestly, if you have a calculator, why not use it? So 891. Of course, we do point out that for the current grade level, you're more likely to get 1 through 6 without the g to the power of h part. Why? Because this matter of using the bigger numbers as the base is not necessarily something they assume you will think of first thing in this grade level. So 3 of these really is enough. Well, that's it for this section. And hopefully we have figured out how to use number tiles, and we have figured out the basis for the distributive property. Oh, yes. Of course, this should really be colored in because it's supposed to be positive. Although, honestly, as long as everything is positive, a lot of teachers can overlook some minor things. So, that's it for this section, and we'll see each other again later.